Okay, so the final frontier is this hat function u with lambda greater than 0. So the equation will let lambda equal k squared equal lambda. So now we get the x squared w plus u w is equal to minus k squared w. Okay, so now we get, if we write this down in these regions, and we're going to get continuous spectrum, we're going to get waves coming in and bouncing and all that stuff, just as before. So if x is less than zeta, it's just the solution we had before with the minus zeta, with the delta function, and I'm going to jump straight to the form here with the incident plus the reflected. And likewise, if x is greater than zeta, we've just got this transmitted. Oops, that should be a plus here. All right, with the plus, the minus here. Okay, so that looks good. So what we've got to do is work out what happens in this middle region, and that's when we get u is equal to b. So in this region here, switch colour, what's the equation? It's the x squared w is equal to minus k squared minus b times w. So we'll call this minus kappa squared w. So we get w is equal to e to the I kappa x, or we can write this, plus b e to the minus I kappa x. We can write these kappas as, we can write these, k doesn't have kappa here. We can write these as sines and cosines, and it doesn't really matter, but it's sort of more convenient, more standard to write that as sines and cosines. And it might be the case here that you're in that region where the thing comes in and you get tunneling, right? This is the case of that inside here the energy doesn't have enough. It can't propagate, so it comes in, it decays, and then you get this phenomena when it bounces, and some's transmitted and some's reflected. All right, so it passes through it, all that kind of stuff. Okay, these are just constants, and we've got sine kappa x. Okay, removing that, I'll just get rid of this stuff here. Kappa is equal to, this time it's the square root of b plus k squared. All right, so, and it's non-homogeneous because we've got this driving term here. We've assumed there's only waves coming in from here, and a reflected wave and a transmitted wave. There's no wave coming out from here. That's not allowed. Okay, so we just match, and there's no even and odd stuff here. You could decompose it into even and odd, but we're not going to do that here. And you end up with a series of equations, and I've written it down as a matrix equation. I'm just going to give you the equations here. So we get at minus zeta, so we've got to match w and the x derivative at x equals plus or minus zeta. So we're going to get 4 equations, right? So the first equation is e to the I k zeta minus plus r e to the minus, sorry, that should be plus, all right, because zeta is minus, r e to the minus I k zeta is equal to b1 cos kappa zeta, because cos is even, minus b2 sine kappa zeta. Okay, so remember these equations are non-homogeneous, and the second equation is we don't So we don't, and the matrix is always invertible. We can always find a solution to it. And we get the solution is these constants R, T, B1 and B2. So then we match the derivative, so we get, it's a bit confusing here, we get minus ik into the ik theta plus ikr into the minus ik theta is equal to kappa times b1 times sine of kappa theta, and this has got a minus, and plus b2 kappa cos of kappa theta. Alright, and then likewise we get, that's it, this is at minus zeta, and we get two more equations at zeta. Okay, we can write them down as a matrix and we can solve that. There's not anything too dramatic about that, and it's not something that I'm going to emphasize too much trying to solve this equation. Okay, I'm going to finish there.